Thanks for joining, and I'm Tasdik. A little bit about me. I have been involved with a couple of open source projects over time in different capacities. Currently, a release lead team member for 1.9 version of Cluster API, a sub-project of SIG Cluster Lifecycle. I also contribute to some of the infrastructure providers of Cluster API, namely Cluster API provider AWS, Cluster API provider GCP, also known to you as Kappa and KapG. In the past, I've contributed to OVER, which stands for Open Source Virtualization, and I work as a senior software engineer at New Relic. That being said, to just start the talk off, a rough outline of what I'm going to be talking about today is we're just going to start with just going through over the pod scheduling primitives provided by Kubernetes, a little bit of background, and what do I mean by that? Kubernetes at New Relic, how do we use it, and what do we use, the different things which we use to make Kubernetes at New Relic possible, and the limitations which we faced when using some of these scheduling primitives in our fleet. And then the later section would be more focused about a solution which we came up with called as scheduling classes, and mostly just goes about the design, how does it work, some assumptions which we made, and a couple of solutions outcomes which we have achieved from the solution is some of them being achieving better instance diversity in compute pool, improving the developer experience, and one of them also being increasing Carpenter adoption, right? And what's next in our roadmap for the same, right? Pod scheduling primitives provided by Kubernetes. So before that, just a quick show of hands if you have used some sort of scheduling constraints to schedule or application pods in your cluster. Just a quick show of hands. I see all of you have used it in some capacity, so I think we can just quickly go through the sites and then. But before that, here's just a test kind cluster with 2 worker nodes and a control plane node for us just to try some things out. Worker 1 has node group worker 1 as the label, and worker 2 has node group worker 2 as the labels. As you can see, it's the labels are already present. And so let's look at one of the constraints which Kubernetes provides for scheduling. So node name, straightforward. There's a node which we have, and the label which we have present is the host name which we are going to use. So test kind cluster worker 2. In the specification of your application, you're just going to use the same. Simple and straightforward. Let's take one step forward. Node selectors, a little bit more flexible than node name fields, allows us to specify the labels of the nodes where we want to schedule the pods at. So you can see that we are just specifying in the node selector block of the deployment specification the label which we want to target. And as you might imagine, there would be multiple labels which could be present, which multiple nodes of this label which are going to be targeted via this constraint of scheduling. Let's take another step forward, and let's try looking at affinity. So this goes a bit forward and provides a few extra knobs for applications to use. And broadly, you can just divide this into node affinity, which describes the node affinity scheduling for pods, pod affinity, which would be describing the pod affinity scheduling rules. For example, if you wanted to co-locate pods in the same node as some other pod, you would probably want to use that. And pod anti-affinity describes pod anti-affinity scheduling rules. For example, you wanted to avoid putting this pod in the same node zone as some other pod, you might want to use that. 2 small things which I just want to quickly add before we move on to the next slide is some 2 other further knobs which you might end up using is required during scheduling, ignored during execution, and preferred during scheduling, ignored during execution. As you can see in this example, we are using node affinity combined with required during scheduling, ignored during execution. And what this constrains the scheduling rule for this specific deployment into the cluster is that we would have to, the nodes would have, when the scheduler is selecting a node, it would have to absolutely satisfy the requirements of the match expression which we are presenting here, which is the architecture of ARM64 and AMD 64, should be present inside the node. And that was just a quick brief. And before we move on to the next, just another quick primer is taints and tolerations. A node has a taint. As you can see in this node, there is a dedicated feature foo, no schedule, taint present, and then the application has to tolerate this taint. So we provide a toleration inside the deployment spec here to tolerate this taint and get scheduled into this node. Right, so that's just a quick brief of different scheduling constraints or ways in which Kubernetes allows you to natively do things. And moving on, a little bit of background of Kubernetes at New Relic. At New Relic, we love Kubernetes and have adopted it widely for a lot of our compute requirements. We currently roughly have 270 plus Kubernetes clusters across different environments, and it's spread across different cloud providers, geographies, regions, and zones. And again, just a few rough numbers. Currently, we have close to 317,000 plus pods across different cloud providers with a maximum of 19,500 pods plus cluster. And for nodes, we are around 17,000 plus nodes in these different cloud providers, and with a maximum of 375 nodes plus cluster, right? So just a quick brief about the background at where we are going to. And so how do we really provision nodes inside? So let's zoom down a bit further into what do we really use to provision these nodes which you find inside these cloud providers, right? So we heavily use cluster API machine pools, and for quick show of hands, people who use cluster API, for example, to use their nodes or provision their nodes. Okay, I see a few hands, but just for others' context, it's a SIG cluster lifecycle project, and it provides a way to manage a set of machines by providing common configuration. There is another construct called machine deployments, but machine pools is different in a way that each infrastructure provider has its own implementation for managing the machines. So for example, the infrastructure provider creates the autoscaling primitive in the cloud provider. For example, in AWS, it would create the autoscaling group, and in Azure, it would create the virtual machine scaling sets, and so on and so forth, right? So most of these things of how to create a machine pool have been abstracted out very heavily from the application user, and they can more or less just deploy a machine pool via our deployment platform, and then are able to track it and make changes to different attributes to it, so on and so forth, to further extend it the way they want their machines to look like. Another compute provider which we use extensively is Carpenter, and let's talk a little bit about Carpenter provisioners. Folks who have, quick show of hands maybe, who have used Carpenter before or have heard, we see a couple of hands. So just a quick brief, it's just one of, it allows specifying the advantage here that Carpenter provides is that it allows specifying different architectures, instance types, and instance families in just a simple configuration, right? And it optimizes for cost by choosing which node to provision or which node to deprovision. And you can imagine that that allows for enhanced bin packing of your applications inside your cluster. Another big advantage which it gives to you is groupless autoscaling. And what do I mean by that is you don't really have to, when a new node is being created, you don't really have to manage these autoscaling primitives which the cloud service providers are giving to you. Carpenter does this behind the scene for you, so it could be of any of the shapes which you have defined inside the provisioner configuration, right? Cluster autoscaler, it's a very important component of every Kubernetes cluster. But in this case, how do we use it is very similar to how most folks end up using it, is that we use it as in conjunction with the machine pools, and it can modify the replica counts of the autoscaling primitives provided by the cloud provider, scales up, scale down, simple, straight and forward. And the assumption made is that just for each of these machine pools, you end up needing to have a similar shape and size, by which I mean CPU, memory, and disk, so that auto-scaling can work better or efficiently out of the box, right? So now the next question you might think is, in a cluster, how would you run them together, in a sense, right? And for this, we ended up coming with a convention that whenever we create machine pool nodes, it's always created with specific nodes labels and taints, which would be then used to differentiate the different sets of machines inside the compute pool. Scale from 0 is implemented, so cluster autoscaler can just scale in, scale out based on the compute requirements of the applications that are trying to schedule into these machine pools. Coming to Carpenter nodes, we don't really add any node labels and taints inside the provisioner, so you can imagine that when the node comes up, there is no specific application label or node, which, apart from the Carpenter labels, getting attached to these Carpenter nodes. And it scales from 0, again. And some of the limitations which, while using these primitives in our fleet, we ended up noticing that let's just quickly go through what could be the limitations, or what are the limitations for some of them. Node names, nodes not constant in the environment. Nodes keep coming in and going out. As you can see that there is a scale to 0 configuration to scale from 0, and based on compute requirements, it might just scale to completely 0 also, right? So node names are not something constant. So if you are putting something inside the application deployment configuration, it's bound to change almost constantly, right? Node selector works pretty good, improvements over node name, and it adds filtering on labels rather than on the node name. So it's definitely an improvement on top, but still becomes a bit challenging when required for more complex scheduling requirements. For example, if you would want to schedule these application pods in different availability zones, you might be finding it a bit hard to try doing that with node selectors, right? And the next thing which would be there is affinity and anti-affinity along with tolerations. This definitely works, and is probably one of the most efficient ways to do out-of-the-box scheduling for your applications. But you will start noticing that as your number of node types, instance families, and different kinds of features which you're trying to provide from these compute pools, it becomes more and more complex for users to pass and configure. And these values might also change over time, depending on the growing needs for the application. So they might need something before, and then they are changing it over time to something else, which is completely possible and a natural evolution of the application. You can see that the application team is going closer and closer to specifying these almost by themselves, which is prone to a few things, which we will discuss in a few slides. So where does that bring us to? So we came up with something, so with the increasing adoption of Kubernetes, we observed a growing variety of scheduling requirements among different teams and applications, which was making it very hard to track and ultimately impairing the ability to introduce changes to the underlying compute platform in a safe and agile manner. And for that, we came up with scheduling classes for which the aim is to solve this for all the users running inside our Kubernetes platform. And it's a declarative way to express scheduling requirements of applications, and they don't really need to, the users don't really need to dive deep into what's really happening inside. And at the heart of it, we are again building on top of the Cubitus primitives. It's an admission controller, specifically a mutating webhook running on all the resources of different kinds, some of them being rollouts, deployments, stateful sets. And what were our design goals for this? Because we wanted this to be working for almost all the different requirements which users were presenting us with for their scheduling needs, right? So we wanted it to be cloud agnostic. We wanted to not reinvent the wheel. We wanted to build on top of the scheduling primitives provided by Kubernetes. And we also wanted it to be a bit opinionated with some sane defaults. Users could opt out of these sane defaults, but we wanted to still provide some sane defaults. Now, Another thing which we wanted to do is we wanted to take a step forward and then think of these scheduling constraints as something which could be changed together to form new rules. And any attachment of these scheduling classes could add or negate already present rules. And we also wanted to be able to assign priority to these scheduling classes so that we would be able to prioritize in the way in which we would want to attach or detach them. And last but not the least, a very important characteristic of this new system was to be that it has to be deterministic in any given case. If we have a list of scheduling classes which are attached to an application, at the end, no matter what, the result should be the same consistently. So how does it work? Here's a very high-level overview of the flow in a Kubernetes cluster where this webhook is deployed and configured. The webhook executes every time the resources of, for example, deployment, rollout, and stateful set are created and updated. It validates the requirements, which we'll talk about in a bit. It validates some precondition requirements. If it satisfies, we progress further, and the application is mutated with the pod template spec by evaluating the scheduling classes requested, which are passed as a special annotation to the application, and the application gets mutated. Now it is up to the scheduler to decide where to schedule it. So we are again offloading this bit to Kubernetes itself, and only generating the scheduling rules at the end, similar to how we were passing it in at the start of the talk also. So when application, so let's go a bit further into what really happens. So when the application is applicable for mutation, we read the scheduling classes passed, we sort them in priority, we apply them in order until the last scheduling class is attached, and then the generated scheduling constraint, we use it to mutate the final application and inject it back to the cluster. Now, as of now, we are only constraining this to affinity and tolerations field of the pod spec. All of this configuration, which you will be injecting over to the application, is stored as a simple config inside the webhook deployment. So each has a group, each scheduling class has a group of tolerations and affinities, which it adds and removes. So you can imagine multiple rules which are present inside. And then each of these scheduling classes are also grouped via a type. So you can imagine different scheduling classes would end up being of similar types. So we would want similar types to be grouped together and then be able to see if they're compatible with each other or not. Some of the assumptions which we are making so that we are a bit opinionated to fit our needs while building this is any application which is having custom affinity or node selectors and tolerations, we are not to process them. And the reason for that is we don't want any existing application to have an adverse effect while we apply these same defaults. And we would delete any of the scheduling class rules which we would have applied before. So this assures us that there's nothing going wrong with the system. We use the core building blocks of an application of deployment, rollout, and stateful set, for example. We don't directly mutate the pods, but rather the controlling block. Applications which are using auto-scaling via HPA, they get attached to an auto-scaling scheduling class. And what does it do at the end is it adds constraints to schedule them to instances of similar shape and size. Some applications using auto-scaling are very sensitive to instance family, to different instance families, and we would want to limit them to only being specifically deployed to the same instance families, but not of different instance families. So which is why we ended up using another scheduling class for that, which we just named auto-scaling scheduling classes. Another thing which we assumed and implemented here, or not, another thing which we wanted to be opinionated about was for stateful set applications, we would attach the CAPI scheduling class. which would target nodes which don't really consolidate that aggressively. As you can imagine that in Carpenter, because it optimizes for costs more often and more aggressively, it would also deprovision the nodes in that manner. So we would want to prevent that for stateful set applications before going hand. And we would want to be able to also configure a default scheduling class to be attached, which can be configured per cluster. Architecture scheduling class also being introduced here if not present. If an application is not passing an architecture, we would just attach something to it so that it can schedule itself. And if it is already passing something as an architecture, we would just pass it over to the affinity. Now you might think, how is it really affecting the applications in the first place, right? So it's enabled for all applications which meet the requirements, and the requirements being that they don't pass their own node selectors and tolerations. And we would automatically attach the default scheduling class unless we are explicitly choosing to opt out of it. And to distinguish between applications which are being managed by scheduling classes, we would use, again, simple K8s constructs, labels, and annotations. A label to denote which are the active list of scheduling classes which are right now added to this application, and another one to just see if the application is managed by a scheduling class or not, right? Now, how does this help us achieve better instance pool diversity in compute pool? And rather, let's ask, why do we need better instance diversity? The reason you would end up wanting to have more instance diversity is to just help you serve your application teams better, right? You can think in the direction that, like, while new instance families, types, and architectures are required, they are also adding performance or cost savings, or some new instance families are also providing you or your application with the necessary requirements for the applications as they evolve over time, right? So you would want to be able to do this in a consistent manner. And how do we do that? Essentially is, as we saw in the last few slides, we are building our compute pool providers based on cluster API machine pools and Carpenter provisioners. And applications can then be scheduled on either of them, right? And how do we end up now increasing the instance diversity without necessarily creating a lot of machine pools at the same time? So for that, we came up with a construct of node groups. And node groups is our grouping of nodes of similar features being provided by different compute providers. The compute providers being cluster API and Carpenter in this case. And as you can see on the left side, this general pool node group would have 3 compute providers, and the pools would be namely Carpenter pool, copy pool, and each of the copy pools have an implementation for one specific architecture. You can keep extending this further, but you get the general idea here that the nodes of a similar node group have common labels and taints, and apart from a few differentiating ones, it's mostly the same, but the ones which are differentiating are to help the scheduler schedule the application in the specific pool inside a node group, right? And how does this help in increasing instance diversity is, first, you could essentially just keep adding all your different node feature requirements inside the Carpenter pool, and then you could have the different architecture requirements for the cluster API pool also at the same time, so that you are able to schedule either on Carpenter or cluster API pools. And the reason for that is some applications might not be really ready to adopt Carpenter, and for that you would have the cluster API pools which are not doing that aggressive of a consolidation. Now, how does this improve developer experience in the first case? As we were looking further back, a few slides before, the application team had to first specify either by the virtue of passing a node selector, or either by the virtue of passing affinity rules, and then also passing probably some tolerations for their application, and take take it to the case now where the application team just needs to pass an annotation for the scheduling class which they want to use. And in this case, for example, it's passing Carpenter and feature foo. And then it's also just requesting that, hey, I'm fine with either AMD 64 or ARM 64. Now, the scheduling rules which get generated would eventually make the scheduler, the Kubernetes scheduler, make it land up on the Carpenter pool, since we are requesting Carpenter-specific scheduling constraints also. Now, take the second example where if the user wanted to just opt out of Carpenter, they are just going to specify copy as a scheduling class and the feature foo. And essentially, now since both platforms are also added as a scheduling constraint, it's left to the scheduler to decide either to schedule on ARM 64 or AMD 64, depending on what the scheduler decides. So how does this help in the long term? It's, again, building back on top of the primitives which are given by Kubernetes. And as you can see, it's a declarative approach, similar to how we were also doing it while passing affinities also, but it's much more simpler. And the user has to remember a lot of these fine-grained node details which are being used inside your deployment configuration, but rather being just abstracted out to a few 1 or 2 lines configuration at the end, right? And the additive negation nature of different scheduling classes, it allows us to mix and match different scheduling classes so that the application is matching up to different node pools of different features as and when required by the application. So we noticed that the developers were starting to adopt this more and more, and we were also getting a couple of other benefits which we are going to talk about in a few slides, which is one of them being we increased our Carpenter adoption via this approach. And how did we do that? With the Carpenter scheduling class, as we discussed that there is a default scheduling class present which we could be configured for each cluster. The default scheduling class for all of these clusters became Carpenter. So any application which doesn't have any any tolerations being passed or any node selectors being passed, it would automatically get attached a Carpenter scheduling class, and with that comes the scheduling constraints for it, and then the scheduler just decides to put them inside Carpenter. Applications, and for unless specified, all of these applications would then be deployed on Carpenter, and then a user has to explicitly opt out of it. And you could see in the last slide that if you have to just opt out, you can just pass the copy scheduling class, and when the scheduling constraints get evaluated and ordered and generated at the end, the copy scheduling class would just negate out the Carpenter scheduling class rules, and at the end, it would just have the copy scheduling class specific rules, hence opting out of Carpenter. What we also ended up doing was we kept the provisioners narrow with the instance families to begin with, and the reason why we did that in the first place is to allow for less frequent consolidation and then slowly expanded. As you can imagine, Carpenter would be having more options to choose its instance families and instance types from, and it would, in essence, mean more consolidation. Again, opting out of Carpenter, some applications wouldn't want to schedule in a Carpenter pool due to different reasons. The rate at which the nodes get consolidated, or the Carpenter pool present doesn't have the node features which the application needs as of now. And for that, as we just described, the application team could just use a copy scheduling class. And what's next in our roadmap? After we put this out for the application teams to use, we sat down and saw, like, okay, the adoption is good. We are able to abstract this scheduling construct from the application teams further away and have them do it a bit in a more hands-off way. What's next for us? And we were also able to increase Carpenter adoption for us. A couple of things which we thought about was we could essentially have the scheduling classes as a custom CRD to allow the application owners to interact with this configuration and add constraints themselves in their cluster, which as of now was more of an operation which we would do as part of every release of this scheduling class construct inside the cluster. Further on, we released only a couple of scheduling classes in our iterations first to adopt the most high usage patterns which we noticed, so as to get the maximum adoption first. And now what we are planning to do is we want to add additional support for scheduling classes for further fine-grained expression of these scheduling constraints and more specialized instance types. So we are going to increase further and further and add scope in terms of having the user not worry about the scheduling constraints and have scheduling classes do that job for them, right? And this again goes further in the direction of having teams not to manage their own pools, but rather us manage the pools so that we are in control of the life cycle of these compute pools as we have described. As I described that the teams have options to use machine pool as a dependency and deploy that via the deployment platform. We would slowly want to start managing these node pools by ourselves rather than the team trying to update the dependencies and so on and so forth. Again, to further enhance the Carpenter adoption, we would want to slowly adapt more features inside the Carpenter provisioners for the new and existing applications. The next thing which we were planning to also potentially do is in our deployment platform, we would want to show the results of these scheduling constrained results when the user passes something right on the dashboard itself. So they don't have to really guess where did my application pod land up, where is it running, and what was the result, and what are the current active scheduling classes attached. As you might have noticed, I was mentioning a couple of Carpenter objects which are called provisioner, and so on and so forth. Carpenter has recently released the version 1 of itself, I think probably last month, and that means it has V1 objects which it has graduated to, and we would want to further adopt our automation and controllers to evolve evolve our installation of Carpenter also to use the V1 API objects. So that's roughly a little bit of our roadmap which we are planning to do. A few references here which I have used for you to go through if you would be interested. And yeah, that's pretty much it. And thank you for listening.
Thank you for the session. So again, if you want to ask questions, use the app. We're using Slido, as you already know that. We have one questions, but I have two next for you anyway. Is there a plan to add topology spread constraints to scheduling class, or is it a different concept?
We do plan to add it. This was one of the considerations which we were doing, but we wanted to just start small and see what gets the job done immediately so that we would be able to move fast a bit and then see the adoption. But definitely this was one of the things which we were planning to think about adding inside scheduling classes. As of now, we mostly play around tolerations and node affinity, and that too affinity and that too in node affinity. But we do plan to explore further of how the other constructs can also assist us in our scheduling needs.
Got it. Oh, sorry. I have two questions for you. So you were speaking about using cluster API components in your deployment. Are you also using cluster API to manage the cluster in their life cycle, or are you just using KP to just, let's say, throw the cluster, and when there's an upgrade time, you're just ditching them and create new ones?
We do use cluster API for a lot of lifecycle management. But we do have a lot of internal automation to upgrade things, move things around, and then also replace things in place, and also create new things. But Cluster API gives us the building blocks for having all of them inside the Kubernetes resource model, and we heavily build on top of it.
Got it. And the last question I have is still around cluster APIs. Have you ever faced some limitation on how many clusters you were able to spread from the same seed cluster? Or do you have to use a seed cluster that deploys smaller seeds one that deploys then the workloads clusters?
So if I understand your question correctly, I think you are asking if we use cluster API and having a management cluster and then multiple child clusters.
Yeah.
Okay, so we don't follow that model. I think this is a separate topic in itself, but I'll just quickly add a bit to that. We end up having the cluster completely managed by itself. So think the cluster API and its infrastructure provider, all of the components and all the objects are living inside the specific cluster itself. So the cluster is self-managed in a way. And that allows us to tear down or create a new cluster as and when required.
Got it. Okay, we're good for the first day. Thank you very much again for this very interesting talk.